Hi there. Welcome to another podcast from We Talk Science. Today I have Dr. Jan Eldridge from Auckland who's talking to me about physics and stars, I believe. Hi, Jan. How are you doing?
Hi, Shiva. I'm fine. Thank you. How are you?
I'm really good. I hope that the lockdown is treating you well, and I hope everything is okay with you. So I just wanted to talk to you. Of course, I found you on Twitter, and I think that the things that you tweet about are very, very relevant and very interesting. I wanted to talk to you about what you do in your work and also how you started. So if you could tell me a little bit about your background and how your interest in physics and astronomy started off, that would be awesome.
Okay, well, that's a kind of a deep question. I read probably too much science fiction when I was young. I remember going to see like Return of the Jedi with my father and brother, and then when we got our first computer at home, I was only about 5 or 6 years old, and so I've always been really interested in like using computers in space and exploring it. And of course, when I was also at school, I would walk home from school and I'd try and get home in time to watch Star Trek: The Next Generation on telly because that was like it wasn't Star Trek like it used to be. It was Star Trek where you used to have the current science would be discussed as like a plot device, and you'd have to understand it. Um, and one of the reasons I knew about electronics and about computers when I was very young is because my dad was interested in electronics and computers. And while he ended up retiring as a computer engineer, he also used to work on telephone exchanges and other sort of things. So he always had that way of encouraging us to use computers. But I mean, out of my brother and my sister, I'm the one who really always used the computer. And if they needed it, they'd have to try and kick me off, which was difficult. But that both those two things together has kind of driven me to where I am today in terms of being an astronomer is as close as you can be to being Doctor Who, and the work I do is very much about using or making computer models of stars, and so it's kind of just like everything when I was growing up that I was interested in has come to being my career as it is at the moment. So it's quite exciting.
I love how you mentioned the most influential sci-fi series on TV in just 3 minutes into this interview. That's brilliant. You're my kind of people already. I can tell. That's
Well,
amazing.
I've just read the book that I've contributed to called Doctor Who in Science, and I wrote a chapter about exoplanets in Doctor Who, and so it's kind of amazing that the other thing that's happened is I've gone full circle now. I've gone to writing about science and science fiction after getting into science because of science fiction. So it's quite exciting. Yeah.
That's absolutely brilliant. So, tell us a little bit more about what you do now. So, I see on your blog and of course on your website that you are essentially looking at the appearance of galaxies, how stars live and die. As a person who doesn't know that very much about physics, how would you explain this to someone like me, for example?
Um, the toughest point with this question is always where exactly to begin.
Yes.
And I suppose there's many things we could talk about, but the one most obvious thing, if I borrow from what Carl Sagan said in Cosmos, is there's a very deep and very simple thought that you can immediately think about stars, and that is our sun is just another star, and other stars are just other suns, but very far away. And so it kind of opens up the entire universe when you think about this thing that we see every day and we kind of take for granted. There's billions of these in our galaxy, and billions upon billions within the universe. And what do they do? Do they just shine there all the time? Why do they shine? And it took a long time for us to actually work out how where the energy comes from to power stars for billions of years. And it's really the energy source that makes stars important because what they're doing in their cores is they're taking hydrogen, the simplest element, and turning it into helium, a heavier element. And if you squeeze four hydrogen atoms together and you make helium, the helium nucleus is lighter. So it's actually lost mass, which means it's lost energy because Einstein's famous equation that I can always safely assume almost everyone knows, which is E equals mc squared. If you decrease the mass, you've released a lot of energy. And so stars make new elements. And for 90% of their life, like our sun, they'll make helium from hydrogen. But when they get more advanced in their age, they end up getting helium cores because they burn up all their fuel. They make a core of solid helium. And then they can go on to burn other elements. And they can burn elements all the way up to iron. And actually, they can even burn all heavy elements like iron, bismuth, uranium. Those also all produced by some type of stars. It's like a jigsaw puzzle trying to work out which elements come from where. But that has something very deep in it as well, because that means if stars make all those elements, and when the universe was created, there was only hydrogen and helium, we're all made of stardust because we wouldn't have the carbon and nitrogen if it wasn't for stars like our sun when they're old. We wouldn't have oxygen if it wasn't for very massive stars exploding in what I'll term a core collapse supernovae. And we wouldn't have iron in our blood to carry the oxygen around our bodies if it wasn't for stars like our sun, if there was in a binary star system, which is very different because we kind of look at our sun all the day and it's a single star on its own. But the most exciting thing I do is to try and model stars that aren't like our sun, where you haven't got the planets, you've got another star orbiting around the star, and so you've got these two stars together, and they can get in each other's way and have really exciting evolution and like events and really exciting explosions. And if our sun was in a binary with another star that's about the same mass as the sun, eventually one day they would actually produce a sun's mass worth of iron. And that's where most of the iron comes from. And that's why it's so abundant in the earth and why we've used it in our body chemistry to carry oxygen around our bodies. And my job is really trying to understand physics in stars because stars are complex, and then trying to piece together how that impacts the galaxy those stars are in, how it impacts the universe that those stars are in, also then how it makes those elements that give rise to us. And I really like looking at the explosions because that's where a lot of the elements, or most of the most interesting elements, most interesting elements they make are formed.
That's really interesting. So, what I'm hearing, from what you're saying is basically you're looking at, suns and how in their life cycle and how they actually could give rise to life. Am I correct?
That's yes. Hang on, I need to work about that and think about that question. How they produce the elements that would then one day, if they were on a planet that was in a habitable zone around a star, a habitable zone in a galaxy, at a time when the universe itself was on average habitable, then you would be able to get life. But because, for example, if there wasn't these different type of stars, we wouldn't have the elements in the different abundance we see them. And so maybe we wouldn't have carbon and nitrogen, unless life would be less likely. But because there is so much carbon and nitrogen because of stars like our sun when they're dying, then we can have carbon-based life forms. And carbon is a very kind of unique chemistry. Trying to talk about when we get life is interesting because one of the fun things with the work I do is while I can talk about how we can work out where the abundance of elements comes from, we can also ask that question of can a star system or can a system of planets around a star be habitable? How long could it be habitable for? How long is our solar system or how long is the Earth going to be habitable for? It's only going to be habitable for about 200 million years before the sun gets too bright and luminous, and then the Earth will become too hot. And we can understand that because we understand stars. And something a colleague of mine, Associate Professor Elizabeth Stanway at the University of Warwick, has done is taken our models, and she's worked out how habitable galaxies are and how habitable the universe has been. And using the same models that can look at our solar system, she was able to understand that the universe itself has only been mostly habitable for about 5 billion years, which is funny because our star is only 4.5 billion years old. So you can see how it gets wonderfully complex because there's so many pieces to that question of why are we here? It's not just, is our sun the right age? Has it got the right elements for life to be able to evolve over all that time? But also, are we on the right time during the evolution of the universe that life actually won't get wiped out by a nearby supernova? And so, yeah, it's all that wonderful complexity that makes me really enjoy the subject I do.
So here's maybe a dumb question. It's like, how would you predict, for the last part that you basically said about, are we in the right time of, our existence? Because obviously we are existing. How do you predict that we are not going to be wiped out by a supernova? I mean, that's sort of, I'm guessing this is part of the code that you've written as well, isn't it?
Yeah. So there's two ways you can answer that question. So one is if you wanted to ask it today, what the chances of a supernova going off nearby that could affect us. We know most of the stars near us that will explode in a supernova. You can go to Wikipedia and there's a list. And I think there's only one or two that are close enough, even though we don't know. We actually don't know how close a supernova has to go off before it's a problem.
Mm.
It could be, but I mean, we're talking difference between, say, 200 to 300 light years. It's that kind of uncertainty we have. But we're pretty safe. Even if, I don't know if you saw recently, lots of astronomers were getting excited because Betelgeuse was getting very faint. And one of the things that everyone was saying, like, oh, what if it explodes? Are we going to be doomed? No, we're quite safe. If Betelgeuse explodes, we're going to be okay because it's hundreds of light years away. It'll be spectacular, but we'd be safe. And there's no other stars nearby. So at the moment, we're safe. But if you're trying to work out when is it likely for us to, because you can, it's difficult to ask for a specific star whether it's always been habitable or not. But on average, you can think of how many stars there are in a galaxy, and you can think how many supernovae there are in a galaxy. And so you can say, okay, how many are close to a supernova? And then you can sort of do an average game. And so you actually here need to combine different model sets, because the models we have are about what stars evolve, how many supernovae you get. So if you form a bunch of stars all at the same time, and you evolve them through time, how many explosions will you get? That doesn't tell you much about the history of the universe. So you have to go to what we term a cosmological simulation, which are models made by someone else, where someone has modeled the entire history of the universe and all the star formation and the galaxies forming and colliding, and then the stars forming within those galaxies. So if you combine that simulation of star formation, so when the stars formed and how quickly, with our models of how many deaths you get, you can work out how many of those stars forming have a chance of being having life around them. And then you've got to think about other things in galaxies that can be nasty. And if you do the calculations and everything's a bit uncertain, so you've got to work things out. But the universe, for about, if it's 13.8 billion years old, for about 9 billion years, it was just too violent. There was too many supernovae going off, too many accreting black holes that made the universe quite unpleasant to live in. So life was very unlikely. But it was about 4 to 5 billion years ago, it became old enough to calm down a bit. And so life could evolve.
That's really interesting. So here's a very, very basic question. When you say the universe kind of calmed down a little bit, what changed?
I've got to remember what the paper that Elizabeth wrote now. This is tricky. It's that you get lower amounts of star formation. So stars evolve at a different rate. So our sun has a 10 billion year lifetime. If we were to look at the lifetime of a star that's 10 times the mass of a sun, it would have a lifetime 100 times less. So it would be 100 million years or so. And if we looked at some of the most massive stars that are like 100 or 200 times the mass of the sun, those have a lifetime of 3 million years. And so if you have lots of star formation going on, so lots of stars being born, you have lots of stars dying too. But if you have, over time, fewer stars being formed, and then you have more stars like our sun that are older, relatively so, but fewer supernovae because you're forming less stars, then the universe just becomes less nasty. So the galaxies have evolved to be bigger and safer. And so they've got more of the old stars. And actually, our galaxy is like mostly safe. But the safest galaxies are actually things we call ellipticals, which have no star formation. And they have like hundreds of billions of stars that are about the mass of our sun. And so that's a very old galaxy. Nothing exciting is going to happen to that galaxy. And it's like if a star was to explode, that would be bad for stars nearby it. And so it's that we just basically got it's like it stopped its wild years. And so it calmed down a bit and it could establish life around its stars.
So, of course, that begs the question, right? If there are less and less new stars being created and more of them are dying, so that basically means the universe is actually getting older. And
Yes.
yes, so how do you? I mean, that's quite an interesting concept, right? Like if there's not many new stars, then we are slowly coming to the end of the existence of the universe. I mean, is that a very bold statement to make?
It's worse than you think.
Okay.
So you're right. Most of the stars that are formed in the universe have already formed. So it's something like 90% of the, I'd have to calculate it to work it out, but something like 90% of the stars that will ever form in our universe have already formed. There's only like another 10% that can form. What's also happening is not only when we think about the galaxies, let's just think about those for the moment and what's going on in the universe. The universe is expanding, and the further away things are, the faster they expand. And so, because everything's flying apart from itself unless it's close. So, like, the gravity can overcome this expansion. It's not really everything's flying apart, it's expansion in the fabric of space time. And so, it can hurt my brain when I'm trying to think about this. But eventually, we won't see any other stars because they'll be moving away faster than the speed of light, and we can't see them. And so, not only have you got not many more stars to form, many of the stars that are already formed are going to be further away from us in other galaxies. We'll only have our galaxy and local galaxies together that we'll be able to see. Now, the last thing to consider in all of this is you're right, that there's not going to be many new stars being formed. But the low mass stars, like our sun, have, as I said, 10 billion year lifetime. If you go down to the minimum mass for stars to form and be a star, which is about a tenth of a solar mass, those have, I think, 1 trillion year lifetimes. I'd have to check that, but I'm pretty sure it's of that order. We don't really know because we don't know what's going to happen because the models of low mass stars are actually quite complicated because they can get so old, really weird effects come into play that we don't have to worry about with younger stars. So we're actually okay because, I mean, while our sun, we've got 200 million years, we could just move, in theory, to a lower mass star. There's one called TRAPPIST-1 where we know that it's on what we term this hydrogen burning limit. It's at the lowest mass and it's got 6 Earth-sized worlds going around it, with 3 of them in the habitable zone. So, that would be the ideal place to move to. And I have seen people talk about like going to try and collect all these low mass stars and bring them together. You wouldn't really need to do that because there's star clusters you could go to where they have millions, got to get my numbers right, millions of these low mass stars that we would be able to use for trillions of years as an energy source. So yeah, So sorry to end up on such a depressing note that we've only got 1 trillion years or two before everything gets too cold.
No, it's brilliant. I mean, it's such an interesting subject that as I said, I don't know very much about. So I'm absolutely fascinated. It says on your website that you've created a unique code, which is called the Binary Population and Spectral Synthesis Code. Do you think you could tell us a little bit more about that?
Yeah, so I mean, it does a lot of the predictions I've just talked about. It predicts those, so it knows the lifetime. If I wanted to actually go and check the lifetime, I'd have to log into my computer in my desk at work, and I could look up the stellar model and look up the age. What's unique about BPass is that it does binary stars. So I never am quite sure why the stellar community for massive stars, those ones that explode in what we term cold collapse supernovae, always went down the single star path, thinking that these must all be single stars. But we actually now know most of them are in binaries. Something like every 3 and 2 stars is binary. So I'll let you work out that, and the audience will go like, hang on, how can we be 3 and 2 stars? It's because with binaries, you only see one star because they're so far away. Unless you look very carefully and look at the spectra of the stars, you think it's 1 rather than 2. And so BPass, at its most base level, makes computer models of how those 2 stars interact. Because like stars like our sun will become red giants, go through a little bit of dying that'll be quite quiet, and then will become a white dwarf, and it's quite boring. But if you're in a binary system, those 2 stars can interact, and if you try and fit a red giant into a binary, but you've got another star nearby, they kind of like get in each other's way. And there you can get some really interesting explosions like a thermonuclear supernovae, which is what I mentioned earlier, that creates all the iron in our blood. And so BPass models that, but it doesn't just do one mass range. It does all the types of stars. And I've tried to make it, along with Elizabeth, to be able to do all the different types of evolution you can get from stars if you have them in binaries. One subtle detail is that those models, there are other people who have codes that do similar things. where they're called rapid population synthesis code, because they make approximations about the evolution of the star by like fitting it to models of single stars. But with us, we actually make a full model of the star, so it's interior from the center to the surface, and we follow all the nuclear burning, which is difficult because with the rapid codes, they take a fraction of a second to model the evolution of a star over its billion-year life story. Ours takes somewhere between 5 minutes to half an hour per model. So if you have a fraction of a second compared to minutes, you realize that then suddenly you need months or years of computing time to actually calculate a large number of models to actually reproduce all the possible things we could see in the universe. So that's why I like, it's a good thing I like using computers, because otherwise I would hate trying to make this large number of computer models. So this is what happened when Elizabeth, we finished our PhDs. I'd been making models of stars. Elizabeth had been studying galaxies at the edge of the observable universe, and she pointed out to me that galaxies are made of stars, and I had all these stellar models. So why didn't I try and predict what galaxies look like? And she had found these galaxies, high redshift at the edge of the observable universe, that looked a bit strange. They didn't match the models based on single stars that people were using. And so after a long process, we found out it was because of a binary effect mixed with binaries being spun up to rapidly rotating that explained these galaxies. But it meant we had to do something called spectral synthesis, which is where the stellar models normally print out the luminosity and the temperature at the surface of the star, but they don't tell you what they would look like. If you took a spectrum of the star, or took a picture with a camera, they didn't tell you what color you would see. And so we had to combine it with stellar atmosphere models that tell you what a star will look like if it's a certain temperature. And then it goes through all those models, and we now predict what we were really, we observe our stellar models just like an observer would go and observe a galaxy, because that means you can compare those two things directly without having to make guesses in the observations. And so because we do all these things at the same time, it means we can compare to many different things. And so I think you mentioned predict what galaxies look like. We do, but then we also predict how many supernovae we should see in those galaxies. I now have a student who is currently working out how many gravitational wave transients we should see. So that's like where you get to the end point of stellar evolution. You have two black holes maybe that have been formed by the two stars in a binary, and those merge and they send ripples through space-time that we can detect. And so we're trying to constrain the physics that went into those stellar models by looking at everything in different ways, by counting things, by taking pictures of things, and by, in some ways, listening to the universe by trying to detect the gravitational waves that are produced by those stars as well.
Fascinating, absolutely fascinating. Okay, well, this has been so incredible. I'm going to change gears a little bit now and just talk to you a little bit more about your experience as a researcher and in academia as part of the LGBTQI community. Do you want to tell us a little bit more about that? Like, what has your experience been? What have your challenges been? You know, things like that.
Yes, and that's always a tough question to ask, because I've become able to be myself, but only once I had a permanent position at university. Like, I hid who I was when I was a postdoc and earlier in my career. I mean, there's two reasons for that. One is I didn't understand myself, which is always the most confusing thing. How can you know who you are if you don't try and feel able to be yourself? But also because then you're worried about whether you'll actually get a job. You know, would you actually be hired for a role with them saying like, "Oh, we can't have them because they're weird, they're unusual, they're not like me." So I mean, that's the worries, and it's. I mean, but since coming out so far, there haven't really been any problems. But then that's because I knew and felt I was in a situation which was safe to be myself. In terms of problems, there haven't really been any. It's opened up quite a few avenues, but I mean, I've also had to deal with things like at conferences where people have posted nasty things on like conference websites that are obviously clearly about negative negative things about transgender people, which kind of affects you because it's like, well, obviously, even though you should be thinking about the science I do, this person was like more concerned about who I was. But the most amazing thing about being myself and also learning about who I am is actually I've been able to work with a bunch of students, or a group of students, I should say, in the university to try and make the entire university infrastructure better for transgender and gender diverse students and LGBTI Takatakapui students. For those who don't know, Takatakapui is the Maori word meaning queer identities. And the University of Auckland now has the full rainbow banner as being LGBTIQI Takatakapui. So the reason we include Takatakapui is it reflects the fact that the equity is a intersectional object. You know, you've got to think about many different levels because people bring many different elements of themselves to work and to study. But it was working with this group of students because I thought that, like, oh, I'm a university lecturer, I can actually help these students with what they're trying to do because I have an enormous amount of privilege. So we could actually make changes within the university, and we've had huge changes within the university, and also they're working with the students and trying to write up all this information. I've learned a huge amount about queer identities and also therefore my own identity. And the kind of things we've achieved are the university will pay for students' legal name change as well as an identity document, which is kind of important to ensure their safety if they need to produce identification in their name rather than using just a preferred name system. Um, we've done many other things in terms of just within the university than recognizing students. For example, if somebody needs to change their name as a transgender person, they'll have a free reprint of their ID card. If they change their name at a later date, they can get a reprint of their university degree certificates. It's all these kind of small things that say the university recognizes a person's identity. And so that's makes you feel like you've actually achieved something. You know, when you're studying stars on the other side of the universe, they don't really care too much. But if you can make a change in a student's life, and so they know that the university recognizes them, so that they know they're okay and they're safe and they can study and do very well in their studies, that's you can't measure how important that is compared to anything else. Um, so yeah, I think it's funny if I look back now and if I realized who I was earlier, would I still be myself? That's always complicated. But there was always this issue, like when I used to be in the closet, as we say, that you had to hide if you were and you couldn't relax. Now today I'm able to be myself. I'm actually much happier and I get so much more work done. And it's just so easy to go to work because I can just be myself without having to hide anything. And I think it's that change that is most important. So that was a large amount of different ideas. So I hope it's useful and kind of answered your question.
It absolutely did. The thing is that I'm very very much into this whole idea of equality and diversity and inclusion. And one of the things that here's a question for you. I think my last question to you would be, as an ally, what are the elements do you think that an ally should have, and how can we help?
Yes, it's a tough question because it depends on who and what the actual each individual person might want at that time. They might just want somebody to listen. They might want you to do something. But at the end of the day, it's just you've just got to listen and know that while you can learn an enormous amount, unless you're in somebody's situation, you can never understand exactly what they're going through. And it's always about lifting up other voices, which is kind of what I've tried to do and make sure that the voices of the students were being heard, the transgender students were being heard, rather than people telling the trans students what they thought they should be doing. Um, so just being ready to listen and realize things are complex and try and think like, okay, so this person is trans, but maybe they're also have a disability, and maybe English isn't their first language, and or maybe they're a refugee as well, and all these things add up, and so it can be, just don't try and think along one axis. It's a multi-dimensional space, and it is always intersectional. And that's like, okay, so that's two things then. Listen and remember that everything's intersectional. And just because one person has come to see you or talking to you or needs help for one reason, maybe it's not as simple as you think because there may be other issues affecting them. But it's a difficult question. Just be ready to learn. And I suppose that's the thing I like about all this work to do with trying to make things equitable and inclusive is that you have to learn because the universe is incredibly complex. Stars are incredibly complex. Galaxies are complex. Turns out people are too. And why should that not be something we enjoy learning about? And it's kind of taken me a long time to realize that it's quite interesting to learn about people and all the different viewpoints we have, just as much as it's fun learning about the universe. So, yeah. Again, I think I went off on a tangent there, but I hope that's useful.
That is incredibly useful. It's a wonderful note to end this interview on. Thank you very, very much, Jan, for your insights, both on stars and on humanity, actually. Thank you very, very much for your time. Appreciate it.
You're more than welcome, Shiva.
Thank you all also for listening, and tune in the next time for another fabulous blog post on We Talk Science. Have a great day, guys.